We're looking at section 13.3. Now we're talking about what happens if our base is the value e. So let's say we've got a function 1 plus 1 over x to the x for several values. So they've given some of them there. And as the value of x increases without bound, the value of f of x approaches a number whose decimal value is about 2.718. This is an irrational number called e. So we can write this in symbols as f of x goes to e, as x goes to positive infinity. So even though e is an irrational number, it can be used as the base of an exponential function. The number e is sometimes called the natural base of an exponential function and is used extensively in scientific and other applications involving exponential growth and decay. So if we find out what these different values are, 1.648, and then 2.718, 4.481, and 7.389. You can graph these, plotting the points. The domain is still, as we've seen, going to be all real numbers. And just like we've seen before, the range is going to be y is greater than 0. So it's going to be another increasing function. The y-intercept is still 0, 1, because anything to the 0 power is equal to 1. The other reference point we're going to use now is 1e. So end behavior, as x goes to positive infinity, f of x is going to infinity. And as x goes to negative infinity, f of x is going to 0 because we have that horizontal asymptote at 0 once again. So what's the relationship between the graphs of f of x? Sorry, f of x is equal to e to the x power, 2 to the x power, and 3 to the x power. So remember, e we said is approximately 2.71. So because e is in between 2 and 3, the function is going to be essentially between 2 and 3. So it's going to be between 2 to the x and 3 to the x. So just like we've seen before, same types of transformations, just different reference points. 0, 1, which is still the same. 1e now will be our new reference point. So we've got 3 times e to the x plus 1 plus 4. So stretched by a factor of 3, we're going to move left 1, we're going to move up 4. So the key difference here is normally we'll leave it, we won't put it in actual number form, we'll leave that in values of e. When you plug it into your calculator to graph, you will want to get the number answer, but to write it, we normally just would leave it as something like this in terms of e. So let's see, if we've got this function here, we want to see how our coordinates are changing. So our x values would need to add 2, the y values get multiplied by negative 0.5, and then we'll subtract 1. So we've got the coordinate 0, 1, that will become 2, negative 1.5. And then the other reference point is 1e, that will become 3, and then negative 1/2 e minus 1. So once you have those coordinates, you can graph those. Domain is going to be all real numbers. Range, we did reflect, so y will be less than the asymptote at negative 1. So asymptote was at negative 1. We had a coordinate at 2, negative 1.5, and then 3. And looks like that point is somewhere around close to negative 2.5. So the function would look something like this when you graph it in your calculator. All right, so how are our coordinates changing? X, y. Our x values will subtract 2. The y values will get multiplied by negative 1 and then subtract 3. So 0, 1 will become negative 2, negative 4. And then 1e will become negative 1, negative e minus 3. So we should have our asymptote at negative 3. Domain will be all real numbers. Range, we did reflect, so y will be less than our asymptote at negative 3. So we want to graph it. Asymptote goes there. coordinate at -2, -4, and then a coordinate at -1, and it's about almost -6. So function's going to look something like that. Now, writing equations, again, it's all based off of those two reference points. Your horizontal or asymptote is going to tell you your k value, and then the point closest to your asymptote is telling you both your, it's going to tell you your, it's going to tell you your h value where you shifted left and right. And then I believe, yep, the second coordinate, the second point that's closest, the point that's further away from the asymptote is going to tell you your a value. So since we write it in terms of e, so this second point here, the one that's further away, this coefficient in front here is telling you that your a value here is 2. So it's actually slightly easier than what we've seen before. So here we can see that our asymptote is at -6. So that means our k value is -6. So the point closest to the asymptote is telling us that our h value is -4. So then the other point is showing us our a value. The coefficient in front of e is our a value. So a here is -2. So once we know that, our function is going to be -2 times e to the x plus 4 and then -6. So our domain, still all real numbers. Range, we can see at y is less than -6. So our asymptote is at 1. So our k value is 1. From the point closest, our h value is going to be -2. From the other coordinate that's further away, our a value is -1. Notice that it's 1 minus e, so the coefficient in front of e is -1. So now we know that our function should be g of x is equal to negative e to the x plus 2, and then plus 1. Domain, all real numbers. Range, y is less than 1 because of the reflection. So we're also able to do some modeling. It's a similar type of problem than with the ones we've seen before. So they're telling us we've got this model here of the Dow Jones market. We're trying to find the value when the function reached about 3,000. So they just did an approximation. Again, I would draw the line at 3,000 and just do the intersect. It could be a little easier. Now, one thing that is important here. So in an exponential growth model of the form f of x is equal to a to the a times e to the c times x, the growth factor 1 plus r is equal to e to the c. So what you have to do, you have to take the e to the power, set it equal to 1 plus r, use that to find out what your growth rate is. Similarly, if you're doing a decay, you do 1 minus r is equal to e to whatever its exponent is. So in this case, to find the growth rate, they took the e to the 0.121, set that equal to 1 plus r, and found that the growth rate was about 13%. So here we've got a different stock index on the Tokyo Stock Exchange. So they're giving us the function there. You can graph it. You'll find that the function is about 15,000 when x is about 12. So it reaches that peak after about 12 years, or after the year, if this is after 1990, it'll be year 2002. So this time it's a decay. You'll notice it's e to the negative exponent, so that means it's going to be decaying. And so that decay will be equal to 1 minus r. So when we come back, we're going to finish this example and then do one more.